Compass and Straightedge Constructions, a supplement to Dr. Bob's Introduction to Modern Algebra 2 class notes on Section 32, Geometric Constructions. The rules by which compass and straightedge constructions are performed are as follows. We start with a line segment of a length which we define as the unit length. For example, we could assume the line segment lies along the x-axis between the points 0, 0 and 1, 0. We can construct other lines or line segments using a straight edge through two constructed points. Given a point P and a line segment of a given length L, we can use the compass to construct a circle with center P and radius L. Given a line segment of a certain length, a line segment of the same length can be constructed on any given line. A point is constructed when it results from the intersection of two lines, two circles, or a line in a circle. Given 2 points, we place the straight edge so that a line or line segment can be drawn through the 2 points. Given 2 points, we can place the compass on the 2 points and create a circle. Euclid's Elements of Geometry depends, philosophically at least, very heavily on the idea of compass and straightedge constructions. In fact, the very first result, Proposition 1 of Book 1, is a demonstration of the construction of an equilateral triangle using a compass and straightedge. The proposition states, on a given finite straight line, to construct an equilateral triangle. This is typical wording for a result in the elements and reflects the idea that a geometric object does not exist unless it can be constructed. The construction proceeds as follows. First, draw a circle with radius equal to the distance between the two endpoints of the line segment and centered on the right point. Second, draw a circle with the same radius centered on the left point. Find a point of intersection of the two circles and connect the 3 resulting points. Since each line segment in the resulting triangle is a radius of one of the circles, then the triangle is equilateral. In our first theorem, we prove that a given line segment can be bisected. As in the previous result, construct a circle centered on each endpoint of the line segment with radius equal to the distance between the 2 points. Find the points where the circles intersect. Join these 2 points with a new line, and the new line then intersects the original line segment at the midpoint of the line segment. As an additional observation, we see that this construction also allows us to construct a perpendicular line to a given line segment through the midpoint of the line segment. More generally, the perpendicular can similarly be constructed through any point of the line segment. We can use the previous theorem to show that any angle can be bisected. First, use the compass to construct an arc through both rays of the angle. Find the 2 points of intersection of the arc with the rays of the angle. Now, join these 2 points to produce a chord for the angle. By Theorem 1, the chord can be bisected. We then draw a ray through the vertex of the original angle and the point of bisection just produced. This results in a bisection of the original angle. We now address perpendiculars. Namely, given a line and a point not on the line, a perpendicular to the line passing through the point can be constructed. First, draw a circle centered at the given point with a radius sufficiently large as to intersect the given line in 2 points. The 2 points of intersection determine a line segment. By Theorem 1, this line segment can be bisected. The line through the original point and the midpoint of the new line segment is perpendicular to the original line. Given a line and a point not on the line, a parallel to the line passing through the point can be constructed. By Theorem 3, we can construct a perpendicular to the given line through the given point. Now, translate the distance from the original point to the original line to find a new point above the original point on the perpendicular as shown. Since the black point is the midpoint of the line segment through the 2 blue points, by Corollary 1, we can construct a perpendicular to the new line which passes through the black point. The new line is parallel to the original line and passes through the given point. We now give a result which we will generalize later. A line segment can be trisected, that is, broken into 3 parts of the same length. First, we draw a new line through one endpoint of the given line segment to produce an angle. We know, for example, that a 60-degree angle can be constructed by Proposition 1 of Euclid. On this new line, we mark off the given unit 3 times. We connect the third green point to the other endpoint of the given line segment and call the resulting line L as shown. We now draw parallels to line L through the first and second green points using Theorem 4. The points of intersection of these 3 red lines then determine points on the original line segment which result in the trisection of the original line segment. Our textbook claims in Theorem 32.1 that if alpha and beta are constructible numbers, then so are alpha plus beta, alpha minus beta, alpha times beta, and alpha divided by beta if beta is non-zero. If this can be demonstrated, then we can show as a corollary that the constructible real numbers form a field. As we will see, the field of constructible numbers are a field between the rational numbers and the real numbers. As a parenthetic remark, the constructible numbers are in fact a field between the rationals and the algebraic numbers. We now go through a proof of Theorem 32.1. If alpha and beta are constructible real numbers, then so is alpha plus beta. We simply take the segment of length beta and translate it onto the end of a line segment with distance alpha marked off on it. This results in a line segment of the desired length. If alpha and beta are constructible real numbers, then so is alpha minus beta. As in the previous result, we simply take the segment of length beta and translate it onto the line segment with distance alpha marked off on it. This results in a segment of the desired length as shown. For the sake of illustration, we assume beta is less than alpha, but this is not necessary. If alpha and beta are constructible real numbers, then so is alpha times beta. This result requires the use of properties of similar triangles. Mark off distance alpha on a line segment as shown. Introduce another line segment through point O as shown. Mark off a unit distance along the new green line from point O and introduce point P. Similarly, mark off distance beta along the green line and determine point B. For the sake of illustration, we assume beta is greater than 1. Connect point P and point A. Draw a parallel to line PA through point B, which can be done by Theorem 4. Denote the intersection of this new line with the extended original line segment as Q. Now, triangle OPA is similar to triangle OBQ. Therefore, 1 over alpha equals beta divided by the length of segment OQ. Hence, alpha times beta equals the length of segment OQ. This gives the desired result. If alpha and beta are constructible real numbers, then so is alpha divided by beta, provided beta is non-zero. This construction is similar to the previous one. As before, introduce a new line and mark off distances 1 and beta. Connect points A and B. Now construct a parallel to the line through A and B, which passes through point P, which can be done by Theorem 4. Denote as point Q the point of intersection as shown. We again use a similar triangle argument. Triangle OPQ is similar to triangle OBA. Therefore, the length of line segment OQ divided by 1 equals alpha divided by beta. Hence, alpha divided by beta equals the length of line segment OQ. This gives the desired result. Theorem 32.1 shows that all rational numbers are constructible. We now give a result which shows that more numbers are constructible than just rationals. If alpha is a positive constructible real number, then so is the square root of alpha. Let line segment OA have length alpha, where, for the sake of illustration, alpha is greater than 1. Extend segment OA by length 1 and introduce point P as shown. Find the midpoint of line segment AP. With this midpoint as the center, introduce a circle with diameter AP. Construct a perpendicular to segment AP through point O, which can be done by Theorem 3. Denote the point of intersection of this perpendicular with a circle as Q, as shown. Join points P and Q and points A and Q to produce a triangle. We know that triangles QAP, OPQ, and OAP are right triangles. Therefore, angles OQP and OQA are complementary. Also, angles OPQ and OAQ are complementary. Therefore, triangle OPQ is similar to triangle OQA. We now have the length of line segment OQ divided by the length of line segment OA equals the length of line segment OP divided by the length of line segment OQ. Equivalently, the length of line segment OQ squared equals the length of line segment OP times the length of line segment OA. Since the length of segment OP is 1, then the length of line segment OQ squared equals the length of line segment OA. Therefore, since the length of OA is alpha, we have the length of line segment OQ squared equals alpha, or that the square root of alpha equals the length of line segment OQ, and the result follows. We now have that the set of constructible real numbers forms a subfield of the real numbers. We will see in class, in Theorem 32.6, that the field of constructible real numbers consists precisely of all real numbers that we can obtain from the rationals by taking square roots of positive numbers a finite number of times and applying a finite number of field operations. We now show that an angle theta is constructible if and only if the length, absolute value of the cosine of theta, is constructible. First, suppose the length, absolute value of cosine of theta is constructible. Construct a perpendicular to the line segment of length, absolute value cosine theta, where the perpendicular intersects the line segment at the right-hand endpoint, which can be done by corollary 1. Construct a circle of radius 1 centered on the left endpoint of the line segment. Connect the left endpoint of the line segment to the point of intersection of the perpendicular and the circle. We now have a right triangle which contains the acute angle theta. If theta is not acute, then we can construct it using the angle constructed here and a combination of right angles. Now suppose angle theta is constructible and let point O be the vertex of the angle. Construct a circle of radius 1 and center 0. From the point of intersection of the circle and one of the rays of angle theta, construct a perpendicular to the other ray of theta, which can be done by Theorem 3. Therefore the distance, absolute value cosine theta, can be constructed as shown. We now explore the construction of regular n-gons. We start by constructing a regular pentagon. Suppose we are given a circle, the center of the circle, and a point on the circle. Construct a diameter of the circle through the two given points. Construct a perpendicular to the diameter by corollary 1, and find the point where the perpendicular intersects the circle. Bisect the radius of the circle as shown, which can be done by Theorem 1. Connect the midpoint of the radius and the point on the circle as shown. Bisect the angle as shown using Theorem 2, and find the point of intersection as shown in blue. Construct a perpendicular to the radius through the blue point as shown using corollary 1. Find the point of intersection of this perpendicular with a circle. Now, connect the 2 points as shown. We now repeat this process by reflecting the process to the left side of the vertical radius. Repeat the process 3 more times to get a regular pentagon. The construction of a regular hexagon is easier than the construction of a regular pentagon. Suppose a circle is given with the center and a point on the circle identified as shown. Construct a new circle centered at the point on the original circle with the same radius as the original circle. Find the 2 points of intersection of the 2 circles. Construct 3 diameters of the original circle as shown. Mark the points of intersection of these diameters with a circle. Connect the points on the original circle to produce a hexagon. In section 55 of Fraleigh, we will classify exactly which regular n-gons are constructible. A Fermat prime is a prime number of the form 2 to the 2 to the k plus 1, where k is a non-negative integer. The only known Fermat primes correspond to k equals 1, 2, 3, and 4, and are, respectively, 3, 5, 17, 257, and 65,537. Theorem 55.8 of Fraleigh states, the regular n-gon is constructible with a compass and a straightedge if and only if all the odd primes dividing n are Fermat primes whose squares do not divide n. Notice that this implies that a regular n-gon is not constructible for n equals 7, 9, 11, 13, 14, 18, and 19, for example. Constructions for regular n-gons for n less than or equal to 20 were given, or implied, in Euclid's Elements for all possible cases except n equals 17. Carl Gauss is the first to show that a regular 17-gon could be constructed. In fact, it was Gauss who first gave the sufficiency for Theorem 55.8, which was proven in its entirety in 1837 by Pierre Wansel. We now address the three geometric constructions from classical Greece. First, doubling the cube is impossible. That is, given a side of a cube, it is not always possible to construct with a compass and straightedge the side of a cube that has double the volume. This is true because, by Theorem 32.6, the cube root of 2 is not a constructible number. Second, trisecting an angle is impossible. That is, there exists an angle that cannot be trisected with a straightedge and compass. This result might seem a bit surprising because we can bisect an angle by Theorem 2, and the construction involves bisecting a line segment, which was accomplished in Theorem 1. We can also trisect a line segment by Theorem 5. However, there is no general straightedge and compass construction to trisect an angle. In fact, a 60-degree angle cannot be trisected, and therefore a 20-degree angle is not constructible. This is because the cosine of 20 degrees satisfies the equation 4 cosine cubed 20 degrees minus 3 cosine 20 degrees equals 1/2. The solutions to this cubic equation are not constructible. They involve cube roots, which are not constructible by Theorem 32.6. And so, cosine 20 degrees is not constructible. Therefore, by the lemma to Theorem 32.11, 20 degrees is not a constructible angle. Thirdly, squaring a circle is impossible. That is, given a circle, it is not always possible to construct, with a compass and straightedge, a square with area equal to the area of the given circle. Performing this construction would require constructing a line segment of length square root of pi. Since pi is not constructible, pi is not even algebraic, it's transcendental, then square root of pi is not constructible, and hence squaring the circle is not possible. References. Of particular interest are chapters 32 and 55 of John B. Fraleigh's A First Course in Abstract Algebra, 7th edition.